Okay. So I wanted to start formal theories today, but since there was some confusion last time about maximal consistent sets, I thought I'll, and since there were some errors in the slides, I thought it would be best to just go through it once and then come to formal theories. Right. So so So, I will quickly go through it. So, you have so we have the notion of maximally consistent sets. Basically what we are saying is, given any satisfiable set of formulae, how many more elements from the language of propositional logic can you add while keeping it consistent all the time, right. So, it turns out that for if you can keep on adding any formula as long as you do not add both it and its negation, right. So, only one of them can be in a consistent set. Okay, the proof of that of course relies on the semantics and a proof by contradiction, and then we defined this general notion called a property of finite character, right. And this is much, it goes outside, it comes from mathematics and it's really got nothing to do with logic, but it is something that can be used in mathematical logic, because satisfiability or consistency of a set of formulae is itself a property of finite character, and that we get from the compactness theorem. A property of sets is called a property of finite character if for any set S has that property P, if and only if every finite subset of S also has that property P. So, our compactness essentially says that S a set gamma is consistent if and only if every finite subset of gamma is also consistent. So, which that is a corollary of the compactness theorem, and so therefore, the notion of consistency itself is a property, consistency of sets of formulae is a property of finite character in the universe of all propositional formulae. Yeah. So, what we had was this, so we had other sort of examples, as I said. One is given the universe of partially ordered sets, which of the sets are totally ordered. So, this property of being totally ordered is a property of finite character, and basically within the universe of partially ordered sets, a certain set is a total order if and only if all its subsets are total orders, all its finite subsets are total orders. However, as I said, the property of, if you take the universe of totally ordered sets, the question of whether a set is well ordered is not something that is a property of finite character. So, the well ordering property is not of finite character, because of the fact that an infinite set may not be well ordered, but all its finite subsets, an infinite totally ordered set may not be well ordered, but all its finite subsets may be will be well ordered, because they will have a minimum element. So, by well ordering we just mean that there should be no infinite descending chain. Yeah. Okay, and other kinds of properties of finite character that you can encounter in mathematics, as I said, were questions like tiling of an infinite plane, k colorability of an infinite graph. So, k colorability is a property of finite character, and basically there is a theorem on the theory of infinite graphs, which says that an infinite graph is k colorable if and only if all finite subgraphs of it are k colorable. Okay, so, and similarly there are things about tiling. So, there is a fairly general purpose lemma called Tukislemma, which allows us to actually extend for properties of finite character a set having a property of finite character to some maximal set still possessing that property, right. So, Tukislemma essentially says that actually Tukislemma is more general. It is not really restricted to denumerable universes, but since in this course we will be mostly restricted to denumerable universes, because we are restricted to languages, and languages are always denumerable. For any denumerable universe and any property P of finite character of subsets of U, any set S subset of U such that S has the property P can be extended to a maximal set S infinity such that S infinity also has a property P, right, where P is a property of finite character. And so, essentially I had made some mistakes with indices, but now I hope I have corrected all the indices. Yeah. Okay. So, essentially what we are saying is, since our universe is going to be is a denumerable set, we just we can enumerate its elements in some order A1, A2, A3, etc. And we can consider an infinite chain of sets S naught starting with S naught being equal to the given set S, assume that S has the property P, and we can construct S I plus 1 as consisting of S I and A I plus 1 if this S I union A I plus 1 has the property P. Otherwise, S I plus 1 is just the same as S I, and therefore, with the assumption that S I has a property P by construction, right. Since we started off with S naught which has a property P, all subsequent S I's will have the property P. All subsequent S I's are also finite, right. So, our infinite set S infinity is just the union of this chain, and what you can prove is that S infinity has the property P, right. And since P is a property of finite character, it is enough to show that every finite subset of S infinity has this property P, right. So, we assume any finite subset T, and because of our enumerations and so on and so forth, this T must be contained in some S I for some I greater than or equal to 0. Think of it this way: T is a finite set, it consists of elements A j, where j is the index in the naturals. Take the maximum index, this finite, since T is a finite set, there must be an element with maximum index, let us say m. Then this T must be a subset of S m, right, for example. And since S m would satisfy P, and P is a property of finite character, T would also satisfy the property P, because T is a finite subset of S m. So, for any arbitrary finite subset of S infinity, we essentially show that T has this property P, and therefore, and since P is a property of finite character, S infinity also has the property. And the fact that S infinity is maximal is very easy. Assume you have some element A which can be added to S infinity. So, you have S infinity union A. Now, this S infinity union A is an infinite set having the property P. P is a property of finite character, therefore, every subset of S infinity union A also has the property P, right. Moreover, since this element A occurs somewhere in the enumeration, it must have some index I plus 1, let us say, right. So, then what it means is that since every subset of S infinity union A has this property P, in particular S I union A I plus 1 would have this property P, but S I union A I plus 1, if it has this property P, is just S I plus 1, and therefore, S infinity is the same as S infinity union this A, right, and therefore, you cannot extend S infinity anymore, and therefore, it is maximal. Okay, so that is what we did, and what Tukislemma essentially says is that given any, and since satisfiability is a property of finite character, essentially any set gamma can be extended or any set delta any set gamma can be extended to a maximally consistent, any consistent set gamma can be extended to a maximally consistent set delta, such that gamma is a subset of delta. And as a corollary, it is easy to see that for any formula phi, either phi or its negation should be in this maximally consistent set, right. Okay. So, Lindenbaum's theorem then follows from this fairly trivially, but in case you want an ab initio proof of Lindenbaum's theorem, that is also here, which I have corrected. So, you should be able to look at it and convince yourself that it is you get a gamma infinity which is maximal and consistent. Okay. Right. So, then let us actually formally start today's lecture. So, what we have actually been doing so far is really delving into semantics of propositional logic. We have essentially been working with the semantics of propositional logic, right. But if you look at logic and its evolution, it essentially started off to formalize mathematics and branches of mathematics, where the notion of a mathematical reality exists only in the abstract, right. Okay. So, one of the things that all our methods have done is like tautology checker or truth table or automated deduction, they are all Tableau methods, for example. So, they are all very useful for automated deduction, okay. But they never capture the flavor of the notion of reasoning, which was what logic was originally meant to do, to capture the notion of mathematical reasoning in such a way that it captures our own notion of reasoning in mathematics in fairly abstract domains, which means that our semantics itself or the models that we are interested in, the abstract domains that we are interested in, do not actually exist except through some language description. Okay. So, when you are talking about the mathematics of a certain domain, that domain is only in the abstract and it is described by some language, by our language. In fact, usually we are using our natural language to describe all of mathematics, right. The point is that we need to be able to reason entirely in that language and still capture the semantics of that mathematical domain without actually having that mathematical domain directly available to us. I mean, that is what mathematical reasoning is all about, right. So, the methods that we discussed directly went to the truth table, which in that sense that mathematical domain was a concrete domain already available to us, and all our propositional logic did was describe just that domain basically. So, all our theorems are essentially of that domain, which let us say is already available as a concrete domain. But if I were to start with a new branch of mathematics on a totally abstract domain which does not have any realization in our so called reality, then I have to describe it in some language, and all the statements about it are also in some language, and the actual domain itself is only the structure of it or the models which satisfy it are only available in the abstract, and they are not available in any concrete form. And yet our reasoning processes are somehow mathematically consistent. So, we want a mathematically consistent theory, right. So, you take let us say take something like infinite dimensional vector spaces or some such thing, the theory of infinite dimensional vector spaces. Where will you go for a concrete semantics? That means the only thing available is your language to describe infinite dimensional vector spaces, and all your reasoning has to occur in that same language. You have to ensure that your reasoning is sort of consistent, there are no circularities in your reasoning, there is a presentation which is logical, okay, and in some stepwise fashion, so that there are no contradictions also. And that is the duty of the formalization of those things is essentially what logics came up for, simply because even in fairly simple domains like Euclidean geometry, the problems of circularity and contradictions were there. And so, the necessity of being able to make what we would call a logically consistent presentation was as important as being able to provide the intuition for the proofs of theorems. So that means now there are two different things happening here. One is mathematical intuition about that domain, you can have fantastic flashes of insight, okay. But the other thing which is not necessarily directly related to the intuition is the presentation of that intuition in some logically consistent manner, without contradictions, without circularities and so on, right. So, that presentation is what you expect mathematics you expect logic to achieve. So, logic is all about reasoning about those presentations, and in that sense, since you do not have the abstract mathematical domain directly with you, except that you describe it in some language. So, the only thing you have really is the syntax of that language, right. So, the actual domain itself is described syntactically, and what you want in your logic is to be able to do that and come out with a formal notion of the process of deduction, the process of proof. So, the process of proof of course is again different from the process of intuiting about properties. So, if I have an intuition about certain properties of that about objects in that domain, that does not necessarily mean that I can present a consistent proof, and that presentation is a different ball game altogether, and that presentation is what we are expecting to do through logic. Yeah. So, we expect to present essentially mathematical theories and formalize the notion of reasoning in a consistent fashion through our notion of formal proof. Okay. So, what we are going to do now is, so what we did so far was essentially the semantics of propositional logic. Now, so now let us assume that we have understood the semantics of propositional logic, and now what we want to know is how to build theories, and describe them in some formal language. So, what we want to do is we want to bring in the notion of a formal theory, and we want to formalize the notion of reasoning in that theory, which is not like the Tableau methods or the resolution method or any such thing, but reasoning the way we do logical deductions. So, there is a process of deduction from certain abstract principles, like inspired let us say by the axioms given by Euclid for Euclidean geometry, or presentations of any mathematical domain, let us say group. The presentation of groups is just in terms of the three axioms of a group, basically the semi group axiom, the identity axiom, and the inverse axiom, right. So, essentially those three axioms say that, well, everything that satisfies these three axioms is a group, and therefore, whatever is derivable from those axioms are the theory of groups, is the theory of groups, and they will be applicable to any group that you might choose, right. And throughout all that you are delving in is you do not actually necessarily have a group available in any concrete form. The group is only an abstract, there are only abstract models of groups available to you. What you have is only a language of presentation and a language of reasoning, right, and we have to formalize that, right. Okay. So, essentially, they do not, so the methods that we have discussed so far, while they are good for automated deduction, do not reflect the process of reasoning that we usually employ, and that is the process of reasoning is called deduction. Yeah? And deduction enables, but of course, there is one thing, deduction enables us to prove the validity of arguments. So, essentially what we are talking about is validity of arguments again, but without actually a semantic model, completely described in syntax, right. So, but the deduction enables proof of validity, but seldom enables proof of their invalidity. I mean, their invalidity construction is still by constructing a model counter example, and so we have to see what to do about that. Okay. Right. So, a proof. So, we will talk about a proof system. So, all mathematical domains essentially have a proof system, So, a proof system for deduction prohibits the use of meaning in drawing conclusions firstly, because we are talking about it as a language of communication, and that is the only language we have, right. Even the model is described in this language of communication. Even if we have a model in our mind, it is only described in that language, and so it is the sentences of that language which actually are the preeminent objects, are in some sense the only concrete objects. There is a similar analogy with programming. It is possible to say that algorithms are abstract objects, they do not actually exist. The only concrete objects that exist are programs. Okay. So, if you look at it in the case of mathematical reasoning also, we are essentially going through a similar process. The actual models that we are trying to describe are abstract objects. The only concrete things that we have now are really the sentences we use to describe those abstract objects. Okay. So, the analogy between and proof is really like a program. Okay. So, but that analogy we may or may not have the time to get into, but anyway, let us look at it. So, a proof system essentially relies on a certain language, and it prohibits the use of meaning in drawing conclusions. It has a number of axioms. So, our description of our mathematical model inspired by Euclid is essentially you have a collection of starting axioms and or axiom schemas and a small number of finitely expressible inference rules. Okay. So, these inference rules will allow us to reason about this abstract mathematical domain. These axioms and these inference rules will actually allow us to reason and prove properties about this objects in whatever abstract mathematical domain we might be interested in describing. There is of course another way, there is of course a way of looking at it, that is that this whole theory itself is like an abstract mathematical domain capable of being described in a meta language. Okay, but that is a different matter, let us not get into it at the moment. So, we want proofs to be non-circular. So, in fact, it would be great if proofs are all trees. Okay. So, or at least directed acyclic graphs. So, dependencies are expressed by proof, but expressed in a cycle free manner, right. So, that is one thing, and the other important thing is, even if this is not we want, since you use a logical language to communicate ideas about objects belonging to some possibly abstract mathematical domain which may or may not have a concrete existence, then what you are saying is at least whoever you are communicating the properties to and the proofs to should be able to manually verify that there is something consistent in your theory, that your theory is somewhat consistent, that your proofs are actually valid proofs, they actually provide valid logical consequences. Think of it this way, you do not have any concrete representation of that of those abstract mathematical objects, and neither the person whom you are communicating with, neither that person has any concrete representation. The only thing that you have available is this language of communication, and therefore, he should also be convinced that the properties you express of this domain are consistent, and all the properties that you derive of this domain have also been derived in some consistent non-circular fashion, right. So, this will lead us to something known as proof theory, but at the moment let us look at formal theories. Yeah. So, there is another thing and there is another thing about this, the in fact if this the last point here says that each proof can be checked manually or verified by machine implementable algorithms. So, this is a requirement which comes actually from the original notion of computation as essentially machine computation as essentially simulating the behavior of a human computer, who does not have intelligence, but has a finite collection of rules at his disposal. So, you can think of this human computer as a child of let us say in primary school or some such thing, and doing computation on pieces of paper. So, in fact, the original model of computation, the Turing machine, was actually inspired essentially by this idea of a human computer who does not exercise intelligence. Okay. So, Turing had a very clear idea of excluding intelligence from it, and so what he is saying is, so therefore, proofs can be checked by algorithms. So, there should be, even if my machines are not intelligent enough to come out with new theorems and new proofs, at least the proofs that I specify should be mechanically decidable by a machine as to whether the proofs are correct or not, whether there is circularity or not, whether it is consistent or not, right. So, the proofs should be checkable, definitely manually, but even by machine, that is a stronger constraint. Yeah. Okay. Many logic books do not emphasize that, but since we are doing logic for computer science, I think it is correct to emphasize that. So, the requirements of a proof system that we are looking at, firstly is that, so we are talking about just a language, so which means it is completely syntactic, right. There is no notion, there is no place for semantics here, everything has to be syntactically represented and syntactically proven. Because of this let us look at the third point, decidability. The correctness of any application which involves a proof, if it has to be manually checked, then you have to be able to check that your deduction process is correct. Each step of your deduction process is correct, and that should be machine checkable. If that has to be machine checkable by an algorithm, and that algorithm always has to terminate, then what it means is that essentially even if you use an infinite collection of axioms, even if you use an infinite collection of rules, there has to be an algorithm which can actually, so there has to be a finitary expression of those axioms and those rules in such a fashion that there is that an algorithm can apply those rules and check that your deductions, each step of your deduction is in fact correct. So, the finiteness actually comes from the decidability. Yeah. So, all we are saying is, we are not saying that you should exclude anything, any infinite collections of objects. All we are saying is that you have to, it should be possible to express collections of infinitary objects in some finitary fashion, yeah, through the means of this language, because every sentence of this language that you are going to use is only a finite string symbol, or in more computer science terms, it is just a finite abstract syntax tree, right. So, each sentence is a finite abstract syntax tree. So, it should be finitely expressible. Okay, the only time when you might want to actually use the semantics is to justify the soundness or the completeness of your system, right. Then at that time there is no alternative except to actually be able to create models and show that your mathematical theory is sort of consistent, and maybe you even have a complete theory. Yeah. So that is when, so this is how we are going to look. So, our focus is really on proof systems, yeah, and the notion of deduction, right. So, now when you look at proof systems and their desirable properties, there are two kinds of desirable properties about proof systems, which are not necessarily in agreement with each other. One which is inspired by essentially Hilbert's axiomatization of Euclidean geometry, and actually is something that we encounter in all our books, when is minimality. That means, I have to be able to expound the entire theory with a minimal number of axioms and inference rules. Yeah, and I mean this comes from the controversy over the parallel postulate, which raged over several hundred years. The question is whether the parallel postulate can be derived from the other postulates of Euclid. So, in that sense, was Euclid's axiomatization of Euclidean geometry minimal or not? So, that was the major problem that David Hilbert tried to address. So, he liked minimal systems, but actually a lot of us we use minimal systems even in computer science, because we use for example, as I said, the specification of groups by 3 axioms is like a minimal set of axioms for groups, right. So, all our presentations are also in terms of minimal systems. So, minimality has its uses. The other thing is naturalness. I mean, is there an intuitive way of doing things, a much more natural way of doing things, and so we will look at proof systems of both kinds. Yeah. So, the first thing to do is to look at a minimal proof system, right, for propositional logic. So, we will define a formal theory. A formal theory consists of, therefore, I mean, so now we are only interested in theories. The actual what they are meant to capture, the actual models of those theories, we are not interested in. We are just interested in the formal consistency and the construction of theories. So, a formal theory consists of a formal language. This is going to be the language of description about possibly abstract objects in an abstract mathematical domain. Yeah. A collection of axioms. So, this formal language, of course, so this formal language has an alphabet, okay, and grouping symbols and so on and so forth, and there is a collection X of variables, a set of operators essentially. We are going to take an algebraic view of most of these things, yeah, and grouping symbols like brackets and so on, if you like, yeah, and what at every point we want things to be machine checkable. That is the important thing. If not machine generatable, at least machine checkable, machine verifiable. So, which means the question of, so this language has to be inductively defined, right. I mean, you can't just create an uncountable set of randomly created sentences. If it has to be machine checkable, it has to be inductively defined. So, which means that typically what we want are finite abstract syntax trees for each sentence in the language, yeah. And inductively defined essentially means that we should be able to apply principles like the principle of structural induction on these abstract syntax trees, yeah, in order to come out with properties of the sentences of the language. And the question of whether a certain string, so this is of course this is a typical non-computer scientist way of looking at it. The question of, you have these grouping symbols and so on, the question of whether a certain string belongs to the language should be decidable. There should be an algorithm to decide it, but essentially what we are saying is, if you say that they have to be, our language is essentially consists of and the sentence, each sentence of our language is essentially an abstract syntax tree, which is inductively defined by this language L. Essentially we are talking about a term algebra, okay. So, you can think of this, that your formal language is essentially a term algebra, right. That is the easiest way. So, then membership and so on, those kinds of questions are automatically decidable. There are simple algorithms to decide. Basically, you have to do tree traversal and check that arities are maintained, that is it, there is nothing else to be done, Yeah. Okay. So, membership is decidable, but it is enough to know that membership is decidable, right. Axioms. So, some subset of this language are going to be taken as the axioms of our theory, right. So, this again has to be a decidable subset, and what do I mean by a decidable subset? I mean that having chosen a collection L prime of L as the axioms, there should be an algorithm which can tell you for any given sentence in the language whether it is an axiom or not. Okay. So, what it means is from this language L you cannot randomly pick sentences and call them axioms. So, there has to be some structure to those sentences, so that an algorithm can work within finite time. Given an input sentence, within finite time it can give you a yes or no answer is to the question, is this sentence an axiom or not. Yeah. So, it has to be a decidable. So, there is a decidable subset of L which are the rules which are the axioms, and then the inference rules, there should be a I mean again our decidability condition means that we cannot have an infinite collections of rules. Our rules have to be some of have to have the finitary property of expressibility, so that there is an algorithm which decides whether I have applied a rule correctly or not. Yeah. So, each rule is just a decidable relation. So, membership in this relation is decidable by an algorithm which can clearly give a yes or no answer. Has this rule been applied to obtain this sentence psi from these sentences phi 1 to phi m? That question has to have a definite answer by an algorithm. It has to have a definite yes or no answer. Okay. So, there is this R should be a decidable relation consisting of let us say R is an Emery relation for some m greater than or equal to 0. So, m could be 0 also, which means then this relation R becomes a unary relation, which also means that it is what is known as an axiom schema. See the fourth point, yeah, it is an axiom schema, but it still remains decidable, everything remains decidable, therefore, manually and machine verifiable, right. Okay. So, for each such ordered pair belonging to this relation R, phi 1 to phi m are called the premises, and psi is called a direct consequence of phi 1 to phi m. Yeah. And usually because of these decidability and other conditions, this R therefore could be an infinite relation, right. I mean it could have a cardinality which is L m cross L. If L is an infinite language, L m cross L is also an infinite language, countably infinite. So, R could be an infinite subset of L m cross L. So, which means that, and if it has to be decidable, then essentially R would usually be presented in the form of a pattern. Okay. So, this does it look like purple color? Okay. This purple color is essentially expresses patterns. These are patterns very much like the patterns you see in a higher order functional programming language. They are structural patterns about the sentences, right. So, we are not talking about string matching, we are talking about pattern matching. So, if R is presented in the form of some m patterns x 1 to x m and a pattern y, then it is a finite representation of a possibly infinite relation, right. So, the presentation of the rule in this form essentially, so these x 1 to x m, these purple variables essentially define the shapes of formulae, what kinds of formula structures can you have, and then having defined the structures, you can then replace all the leaves which contain these purple variables by any formula in the language to get but as long as you replace the same variable by the same formula, you have to get an element of this relation R. Okay. So, we will see that. So, our inference rules have a so one way of finitely finitely presenting infinite relations is to use pattern matching. Okay. So, an axiomatic theory. So, these are the ingredients of a formal theory, and essentially we will say that a formal theory is axiomatic if there exists an algorithm to decide whether a given well formed formula is an axiom or not. Yeah. So, that many of these concepts were defined before computer science was even thought of, and so they express peculiarly. So, they made several distinctions, but I am not going to make those distinctions. So, I am only interested in axiomatic theories. Yeah. Everything that I am talking about should be decidable, and we are also in an enlightened age where pattern matching is something we are all familiar with. We have all done a huge amount of pattern matching in our programming, and so it is easy to understand these things as patterns. Okay. So, the syntax and decidability issues essentially dominate all this, though it is not easy to make out from a traditional logic book that this is what they mean. Yeah. Okay. So, and of course, a deduction has to be finite, because any infinite deduction cannot be verified, only finite prefixes of it can be verified. So, that okay. So, the other thing is that these deductions of a formal theory, since everything is syntactic and pattern matching, these deductions of a formal theory actually can be generated by a machine. Everything is syntactic. So, in fact, these deductions are what might be called the set of formal theorems. I have put theorems within quotes for a specific reason, because I will define the notion of a formal theorem, which will look slightly different from what we normally understand as a theorem. This set of theorems is actually what is known as a recursively enumerable. Okay. And what recursively enumerable means is just that there exists an algorithm which, not that it will always terminate. Take there exists an algorithm, but with which in finite time will generate the next element. Okay. So, it is not really an algorithm in the sense that it is not guaranteed to terminate, but it generates theorems. Let us talk about generation of even sentences in a language, a formally in an inductively defined language. I can think of this language, also the sentences of this language also as being enumerated by first enumerating all the leaf nodes in some one node abstract syntax trees, then maybe 2 or 3 node abstract syntax trees, and so on and so forth. But if I have an infinite number of possible variables, then of course, it is never going to terminate. Even the generation of one node abstract syntax trees is never going to terminate. But all we are saying is that if there is an ordering of those on those variables, if there is a total ordering on those variables, then between any two variables there is only a finite amount of time which this algorithm will take to generate the next one. So, that is so for those of you who have not done theory of computation, the notion of recursive enumeration is that even if it is an infinite set, it is possible to write a program which is guaranteed to spend only a finite amount of time between the generation of subsequent elements of elements of the sequence. I mean, take a simple program, let us say, for generation of all the primes. Okay. So, if you are going to generate all the primes, you are not going to terminate the program, you are going to put it in some infinite while loop or an infinite recursion. But if your algorithm is correct, then the generation of the n plus 1th prime takes only a finite amount of time after you have generated the nth prime. So, the primes therefore can be recursively enumerated, in the sense that there is a program which in finite time will generate the nth element of the sequence and will not take more than a finite time. it is guaranteed, and given the nth element it is guaranteed to produce the n plus 1th element in finite time, right. So, that is a notion of recursive enumerability loosely speaking, and essentially what we are saying is that these deductions therefore, so in theory it is possible with just the notion of machine verifiability to have essentially a non-deterministic program which uses all these methods to generate theorems of a formal theory, okay, in such a fashion that it takes only a finite amount of time to generate the next theorem. Yeah. So, you can order the theorem some way you like, one step theorems, two step theorems and so on and so whatever, and based on some ordering it is possible to generate all the theorems, and that is so the theorems of a theory, formal theory, are recursively enumerable. Needless to say, if your theory is consistent, then your theorems should be truths about that mathematical domain, right. This recursive enumerability only gives me an countably infinite collection of truths. The actual mathematical theory might have an uncountable number of truths, right. Take a mathematical theory relating to the reals, which is already an uncountable set. It is possible there are an uncountable number of truths which I cannot unravel in just countable amount of time, right. I mean, so these are some issues with formal theories, right. I mean, these are some of the things that make mathematics still a viable profession. I mean, we cannot leave it all to the machines. Yeah. Okay. So, the first proof system was actually given by Hilbert and Ackermann, and this is a presentation of this Hilbert proof system for propositional logic. It's so the first thing of course is it is minimal in several ways. One is that the language itself is minimal, it has only these two operators, but we know that these two operators are functionally complete, right. They form a functionally complete set, they are adequate for all of propositional logic. So, all other operators can be defined in terms of these two as some kinds of abbreviations, right. So, given that your actual language of description consists of only these two operators and the set of atoms, the infinite set A of atoms, then you have these three axiom schemas. Okay. Do not ask me how Hilbert thought of it. To this day I have no clue how he came up with this, but there is an interesting thing to these axioms. Does anybody notice them? So, Hilbert came up with these axioms, and 100 years after he came up with these axioms, there is something very interesting about them. And can any of you tell me what is interesting about them? Yeah, I still do not know how he got them. I mean, Hilbert died without, he was too busy publishing too many papers in too many different areas of mathematics to tell us how he came up with them. But this is actually it may not just be Hilbert, it is called the Hilbert-Ackermann proof system. But the whole style of coming up with a minimal set of axioms is called a Hilbert style proof system. Do you see anything interesting in this from the standpoint of 21st century about these axioms? Does anybody know why I have called this axiom S? Can anybody guess why I have called this axiom K? Have you done the lambda calculus? Have you done the typed lambda calculus? Okay. Let us take this lambda term. What is this lambda term? You have forgotten your programming languages, huh? Oh, okay, true or false, okay. It is actually true, but that is only one particular way, but there is a something more fundamental about this term besides being true. It is called the combinator K. Okay. What is the connection between this combinator K and this axiom K? You have done some. So, this is the combinator K, right, and there is also a combinator S, right, and in fact yeah. What is the connection between this S and this axiom S? No idea. Have you ever tried to find the take the lambda calculus of simple types or even polymorphic types, it does not matter. What is the type of K? It takes x which may be of type alpha and it produces a function lambda y x which is essentially a function of this type, right. Now, what is the connection between this K and this K? The types are the same. I mean, so there is an isomorphism actually on the types structure which is like propositional. I mean, the only thing about the lambda calculus, oh by the way, if you must have also learned that this K and S combinators are sufficient to describe all computable functions. Okay. So, every computable function can be expressed in terms of these combinators K and S. It is an amazing result, but the interesting thing is that the types are actually like propositions, and this K and S essentially can describe all positive. So, this n is separate, let us not talk about that. So, the K and S here essentially can give you all propositional tautologies which do not have negation occurring in them. Okay. It is an amazing isomorphism between these two sets, but the even more amazing thing is this rule of inference modus ponens. What is amazing about this? You take any lambda term, you take a lambda term T which is of type alpha arrow beta, and you apply it to some term u which is of type alpha, and what you get is an element of type beta, right. So, you get a new element, a new lambda term v which is of type beta, and this modus ponens exactly captures beta reduction. Okay. So, there is an amazing, I mean it's these things were done independently, though the lambda calculus itself and combinatory logic came up a few years after Hilbert's axiomatization, but the connection is absolutely stunning. You know, the fact that you can all types suggest propositions is quite an interesting thing, and there is an isomorphism between this and modus ponens, which is a standard rule of inference. What if I have proved that something implies something else, and if I am given the antecedent, then I conclude the consequent, right, and that is also beta reduction, right, the type of beta reduction. So this is all that you require, and so there is I will not go into this and its connection with the lambda calculus, that is a little complicated, but let us live with this. So that is why I have called these axioms S and K. Not many books, not many logic books call them S and K, they call them A1, A2. I mean, it is a ridiculous thing to do, but and this modus ponens is actually beta reduction, right. So there is an interesting connection between therefore programming languages and logic, that it's okay.